Okay, so welcome to my talk about the visual logger. Just before we get started, a quick show of hands. Who knows what the visual logger is? Yay, lots of people. Okay, keep your hands up. Keep your hands up if you've used the visual logger. Keep your hands up if you've used the visual logger for something that wasn't AI. Hey. Okay, so hopefully everyone will have something in this talk, whether you've used the visual logger or whether you're completely new to it. We'll talk you through all the way from the beginning about what the visual logger is and some of the ways that we used it at Rare for non-AI purposes. So there'll be a bit of AI in there as well. Also, we're going to talk to you a little bit about why you might want to visualize things from a gameplay point of view as well. I've got quite a bit to get through, so I'm going to go pretty fast, but there's lots of videos, so hopefully you'll find some stuff to keep you entertained. Quickly, just by way of introduction, I was here at Unreal Fest last year, so absolutely honoured to be welcome back again. Did 2 talks, one on Sharks and one on the Kraken. The Sharks one's on YouTube, so if you want to check it out, feel free. I'll reference a few of them here. So my name's Andy Bastable. I've been making games for about 20 years now, which I think qualifies me for veteran status. I'm pretty sure I can unlock that one now. I'm principal gameplay engineer at Rare, so I've got background in AI and animation systems, but the way that it works at Rare is we don't really have an AI team, we don't have an animation team, we have kind of gameplay teams. So we work on lots of varied features, some of which may include AI or animations, otherwise it's kind of more traditional gameplay stuff. So I've done kind of a bit of everything. And previous to that, I've worked on games such as DJ Hero, Guitar Hero, Kinect Sports, and Sea of Thieves. Just in case you don't know who Rare are, I'm hoping that most people do know who Rare are. We're a first-party Microsoft studio. We're based in the Midlands, kind of near a little town called Twycross. It's kind of about like 20 minutes, half an hour away from Birmingham, so smack bang in the middle of the UK. And it's got these beautiful grounds as well. You can see some pictures there. It's quite lovely. And so I'm going to talk to you a little bit about Sea of Thieves, but I mean, the actual title's not that important because actually we're talking about how to use the visual logger in a kind of gameplay thing. But just in case people don't know what Sea of Thieves is, it's a shared world pirate adventure, so that means it's a multiplayer game where people are coexisting in the same world. It was designed from the very start to be service-driven, so we always intended to update it regularly, and we have a big anniversary update that's coming out soon, which is adding lots of things. So the game's been evolving over the past year or so. We've got Xbox and Windows 10 clients and dedicated servers that are hosted in Azure. So the servers themselves are very performance-constrained. They run on a single core. And we developed it using a customized version of Unreal 4.10, or rather we shipped it on 4.10. We actually started on 4.6, and then we customized it so much that actually we couldn't start taking any future versions, which actually makes me very sad because I see all the cool stuff that's coming in 4.22 and 23, and we can't kind of actually use some of that stuff here. So what is the visual logger? So the visual logger, just so that everyone knows from the start, it is a timeline of events. So it is a way of recording when certain events that happen, and they have associated debug, rendering, and logs. So as certain events happen, you can capture them, and then you can visualize them, or you can record some information about them as they go. So you can start and stop recording at any time. You don't have to have it active. So you can, if you're particularly trying to capture a particular bit of gameplay, you can just start it and stop it at the right time. And it's got built-in visualization for a lot of common AI behaviors, which is why I kind of asked about AI at the start. A lot of people, when they come into Visual Logger, they use it for debugging AI because it's got a lot of built-in visualizations. But actually, as a tool, it's a lot more powerful than that. And what I'm trying to do is bust it out of its little AI prison. How to use the Visual Logger. So if you haven't seen it, it's available under Developer Tools. You can see it down there. Handy little red arrow to show you how to get it. And once you've got it up, it will actually open up a particular window, and pretty much like any other window in the editor, it can be docked. So I tend to dock mine towards the bottom so that I can use it. This is what the visual logger looks like. So this window can be docked. So you can see at the top there, we've got the timeline. So on the left-hand side there, we have different actors that the logs can be associated with. And then you can see that we have a timeline there. So you've got time along the bottom, and you've got certain events that are being recorded there. The thick blocks there, you see slightly thick kind of blue blocks. They're actually multiple frames. It's just that you can't zoom in and see them there. We have an info pane down here, so this is really useful. This kind of shows what the states are of particular actors that are in there. For AI, this may be what behavior tree is being processed, kind of what the state is, what the settings are in the Blackboard. It can be anything, and we can write into that, so you can write your own custom kind of visualizers for that. And then you have the debug logging pane as well. So this is really simple. This is actually just channeling the similar kind of logging that you get in the console log or Visual Studio, but crucially, it is restricted to those actors and that time, that event that you have highlighted. So rather than having a massive long log file that you have to parse through and try and figure out which object that refers to, you have them all nicely filtered as part of the visual logger. And then lastly, you have a debug rendering in the scene view. So if you want to, and if one of those events actually has some debug kind of drawing, then that's recorded there, and that will be in the scene view. Interestingly enough, that will the debug drawing will be there if the game's running, but also if the game's not running. So you can stop the game and then go back through the timeline and see all of the visualizations that are there. So quick demo of just how to use it. So here's the visual logger. I've just started it recording, docked it down at the bottom so that I can see it. And then I'm just going to use a little console command just to spawn a chicken. We have a little chicken running around. Hello, chicken. And then you can see straight away it started recording some events that are down there. So if I stop it recording, we can have a little look at some of those. You can see that it's got some debug drawing visualizations up there as well, but it's also got some associated logging. And we can see here, this is it's actually showing some of the EQS points. So this is the way that AI selects points that it can move to. And as you scrub through, you can see that it's actually then also drawing the navigation. So this is the nav mesh here. So the actual content of that is not that important. I just wanted to show you how it works so you can see that there are certain kind of debug visualizations you can have there. I'll talk a little bit about EQS in a little bit, but just to show you that's how that works. Crucially, and this took me a little while to figure out, you can zoom in using the mouse wheel. So if you hover specifically over that little track where the time is there and then use your mouse wheel, you can zoom in, which is super handy because if you have a number of frames that are really close together, it can be really fiddly to actually find the one that you're interested in. And you can see here, if you zoom all the way out, you then get a much broader picture of all of the events that are there. So that's just a little quality of life tip for you, for any would-be visual loggers. So let's write some visual logging code then. So this is aimed at the engineers here. If you want to actually visualize something, let's just show some really sample code. So assuming you're going to add some visual logger to an actor, maybe you've got an actor class. So the very first thing you're going to do is you're going to include the correct header file. So visuallogger.h, really simple, just add that in at the top. You'll need a log category. So anyone who's done any kind of debug logging, you'll probably have one of these already. If you haven't, it's really easy just to create one, just call it your own thing, or that you can use log temp, which is a global one that anyone can use. And then sample bit of code. So this is just a little console cheat, which I've knocked up, very kind of just a toy example. I'll talk you through the various different bits you need of it. So the important bit there is you need the define guard, so enable visual log. That's actually brought in as part of the header file. You're going to need that bit because it's the visual logger is not compiled in on shipping. So if you forget those define guards, then you'll blow up your shipping build, and probably a build engineer will come over and shout angry things at you at your desk. You need to check to see whether the visual logger is recording. To be honest, I imagine this is safe. If you don't check it, it's not going to pollute it, but I can't imagine why you would want to do anything kind of processor intensive if the visual logger wasn't recording anyway, so it's a good idea to put this in. And then you've actually got the logging itself. So these are the actual bits that are doing some logging. This is a really simple example. It's debugging. It's going to draw two locations and a segment, a line segment that's going to join the two together. So the bottom circle is going to be a blue sphere. We're going to have a green sphere, and then we're going to have a little red line, just kind of connecting the two together. So that's really simple. It's just a really simple bit of code there, and I'll show you what it looks like when you run it. So we just start it recording, and then I'm just going to run my simple cheat command, sample visual log, and we can see there it is. So it's in the scene view. And so like the game is running at the moment, and I'm running around, and it's there. I could stop the editor, or I could eject, and I could fly around, and I can see it that way if I wanted to. And if we want to, we can just log text. So we don't have to do debug rendering, because as I said, there is actually considerable advantage to just doing debug logging of your text, but using the visual logger so that everything is grouped according to the objects and the actual timeline that it happens. So just logging text can be really useful. So sample bit of code. I'm just going to throw the code up here. The engineers, I'll give you just a couple of minutes just to see if you can figure out what this is going to do. If you need a hint. And we can see that when we actually run this command, it's going to log out some text for us. It's going to create some nice bits of things. And we haven't got any audio. The audio is playing. Can you imagine Rick Ashley singing this as we scrub through all of the logs that are down there? You can see that it's basically put loads of entry blocks in there, and each one of those has got the text that we've logged out. And indeed, this is actually what the behavior tree stuff does. So this is, again, when it's really powerful for the AI stuff. The behavior tree logs out a bunch of stuff. Now, this stuff doesn't normally come out in the console log. So when the visual logger is recording, you're already getting a lot more information than you would normally do in the console log. So what else can you draw with the visual logger? Because we've got locations, we've done segments, we've done text now. Well, actually, there's a whole bunch of primitives available. You can actually see in visuallogger.h, you can actually see there's a whole bunch of ones here. I've kind of faded out the bottom because there's so many more that I couldn't actually fit it on screen. So we've tended to use the kind of standard primitives. So we've tended to use capsule, box, cone, cylinder. You can also use meshes. I've seen mesh in there. Now, we've not used it, so disclaimer, use it at your own risk. I'm not sure why you would want to use it, but it's there if you want it. So, what did we visualize on Sea of Thieves? Actually, why did we kind of visualize some of these things? Now, as a gameplay engineer, often your complicated gameplay and your algorithm, they're only as good as your ability to know what it's doing. So sometimes it can be really complex code. And in a game like Sea of Thieves, where we have all of these emergent interactions, it's really important that we can actually reason about what's going on. And the way we do that is by able to visualize stuff so that we can actually see what's going on. So we started off basically by extending the EQS visualization for AI. So EQS, if you're not familiar, it stands for Environmental Query System. It's a way of being able to write queries. AI tends to use it, but actually we don't just use it for AI. We use EQS for lots of things. It's technically listed as experimental, even on the latest release, but we've totally shipped a game with it. So go knock yourself out, it's good. So the first thing we started doing was we had line of sight kind of checks for some of our AI, and we thought it would be really interesting to visualize where some of those ones are being broken. So here we can see, this is actually from my Shark talk last year. You can see that the blue points there have been filtered out by the AI. It's trying to pick a point. And the reason it's filtered those out is because it's failed a test called trace by profile. So it's doing a collision test. So it's basically seeing, can I actually see that particular point? So what we started doing was adding in those red circles there so we could visualize where it was hitting. Because originally we couldn't see where it was hitting, particularly if it was getting snagged on bits of geometry. So just by adding that visualization, we were able to understand a little bit more about how it was working. Once we did that, we realized how easy it was to do. We started visualizing more stuff. So one of the things that we did was start visualizing our water height queries as well. So Sea of Thieves has an awful lot of water. We have a complicated fast Fourier transform algorithm, which is often doing water heights. Here we can see that this is actually from a chicken. Chickens aren't allowed to go under the water. And so these are a bunch of points that it's testing. They're under the water, and so what we do is we put the little red, kind of almost like a buoy, floating on the surface of the water so that we can see why it's filtered those out. Now, in this case, it's really trivial because the water is flat. It's in what we call one of our calm water zones, but we often have really choppy water that is changing all the time, and the editor is still rendering this. So being able to log out where those water queries were, again, helps us to reason about what our code was doing. Visualize shark path following. So I did a talk at Unreal Fest last year all about how our sharks do these kind of really graceful kind of moves, and it's really handy to visualize those things as well. So this is kind of beyond AI. This is more into animation. So the sharks pick a point using an EQS query. So here we've got just right at the top, you've got a little kind of red marker that shows where the shark is at that point. And it's picked a point just down on the bottom right. So just down where it says winner, that's the point that it's picked. And so what we do is we generate a curved path that it's going to go to. And it would be really handy to visualize that. So we can just visualize it. What we do is we simulate that move ahead, and then we draw it out. So at the point in which the move is confirmed, we just simulate ahead and then render out where that path is. So that then when we scrub back through the visual logger, we can see the decision-making process, which is the EQS, and then we can see the path that it is confirmed to. This is kind of like the skeletons do when they're doing their pathfinding. They visualize what path they're taking. Here's a little video of it going. The game is actually still running at the time, so just ignore the shark kind of mashing up the player there. But as you go through, you can see these are the EQS points it's doing, and then it's visualizing those paths as it goes. This is actually quite handy because its idle behavior is to go around in loops, but when it attacks, it goes very fast in a straight line. And you can actually visualize as we're going around, it's just kind of moving around in these nice arcs, and you can zoom in on them so that you can see exactly where it is. But then as we move on a little bit further, we'll see that it actually visualizes some of its attack vectors. So there you go. So that was actually where it was swimming in and going in for a bite. So it's quite handy to be able to go back through time and being able to see what it's doing. And because it's in 3D space, it's really handy. You can check to see that it's kind of pitching up and down correctly, which is super handy if you accidentally get your maths wrong and create Sharknado. Which we did. Fortunately, we didn't ship that. So, visualizing the Megalodon bite. So, the Megalodon, just in case anyone doesn't know, we added the Megalodon in our Hungering Deep update in May. The Megalodon is this massive giant shark that attacks boats. So one of the things that this is different from our normal sharks is the bites have to look frightening. So they have to land on boats and they have to give this real visceral feeling of terror. So in order to do that, they need to land on the side of a hull of a ship. So we have a complicated kind of quick approximation to find out where the hull extents are. We do this in Excel. A little tip for any would-be kind of gameplay engineers, do as much kind of algorithmic stuff as you can in Excel. The iteration speed's brilliant. You can visualize it quite nicely, and then you can kind of put it into code. So here we can see we kind of have a bounding box for a boat. From that, we use an inner radius and an outer radius, and then we use the dot product to generate this kind of really nice kind of hull extent. So it's really simple. It's just a couple of multiplies, but it gives us this really nice kind of where the boundaries of the ship are. And based on the speed of the approach, so based on the speed that the Megalodon's coming in, we know its speed. We need to time the bite animation so that it lands right on the edge of the hull. If we start the animation too early, obviously the animation has a particular time. If we start that too early, then the bite, the actual jaw close, is going to happen before the shark has actually reached the side of the hull. If we do it too late, then the animation plays right through the middle of the boat, and you don't get the effect. And so we can see here what happened is at the point in which we do the attack, in order to visualize it, we go ahead and we simulate all of the different possible attack angles that we could have in order to check that our algorithm is working. And the green line right at the top is our actual attack vector so that we can see what's going on. Obviously, we only do those calculations when the visual logger is recording. We don't do those calculations normally. It's just so that we knew to check to see whether our algorithm was working or not. And of course, once it's there, you might as well just leave that logging in because it's always quite handy to see. So here's a couple of videos from streamers showing the effect actually in action. Apologies, there's a couple of naughty words in there. They got a little bit carried away, but hopefully it will show you the effect that it has and kind of how well the actual system worked in the end. Oh, there's no sound. Oh. Okay, well, you'll just have to see that the bite landed really nicely, really satisfyingly on the side of the boat. And then once more again, we can see here comes the Megalodon. Its bite animation's already started playing, and then crunch, smack bang on the side. So that looks quite nice. So leaving AI aside completely, it would be quite handy for us to visualize our projectiles. So we have projectile weapons. We've got flintlocks. We've got what we call the Eye of Reach, which is kind of like a sniper rifle, and we've got a blunderbuss. Now, all of our weapons use a time-of-flight system, so we don't have instantaneous projectiles. We simulate our projectiles. They're subject to gravity, and that means we can visualize them, which is really handy. We can actually see where they're going at any particular point. And this is particularly handy, as we'll see a bit later on, in actually tracking down some gnarly network bugs. So this is a little video of just debugging some projectile fires. So I switched to the flintlock. I'm just going to fire a shot. There we go. We can see that it's already added some traces down at the bottom. We've actually got 4 tracks there. One is actually the weapon itself, just saying this is where I'm aiming at. But if we go through, we can actually see some of the projectiles here. So the top one here is the client. We can actually see, if I just eject and move out of the way, little purple dot is the client there. We can see, there you go, it's simulating that projectile moving. which is quite handy. And then if we look at the bottom track as well, this is the server, which is a little bit delayed because obviously the autonomous proxy, the client, is simulating ahead of the server. Now, what's really useful is you can highlight multiple tracks at the same time. So we can actually overlay the server and the client together, which is really handy because then you can visualize. And we can see there that the projectiles kind of hit that bit of the wall, and that was where they stopped. Visualizing tentacles. Oh, golly, this is rather sea creature heavy, this talk, isn't it? I just realized this. So we have tentacles. We have Kraken, this mighty sea creature that also attacks boats. Now, our tentacles are built up of collision capsules. That's how they work on the server. We don't run animations on our server, so we run a very kind of simplified collision capsule animation. So this is actually what they look like in runtime. This is using real-time debug rendering. This isn't using the visual logger. But you can see there that these are the capsules that it's made up of. Naturally, because they're capsules, and capsules is one of the primitives that the visual logger does, we can visualize those so that when we can effectively record what the tentacle is doing. Now, actually, in 4.10, there was a rendering issue to do with capsules. It didn't kind of obey rotations very nicely. That was what it used to look like on the green, but we fixed it on the yellow. Now, the only reason I mention this is not because, oh, no, they've made a horrible mistake and we had to fix it, but actually, one of the great things about Unreal is if you've got the source code, you can follow all of this code through. And actually, it's not overly complex. You can understand what it's rendering and then change it. And you can also then effectively add in your own rendering, and you can change the rendering so that it's customized to your needs. And this is what we did in this particular case. So you can see here we can render the collision capsules really nicely. How did we use the visual logger then to debug network gameplay? So Sea of Thieves is a shared world game. We have dedicated servers and we have clients. The server is the authority, but obviously it's an invisible server. We don't always see what's going on. The good thing is when you run the editor, you can spin it up in dedicated server mode, and it will run up two separate processes. It will start up the server process and also start up the client process, but they're both feeding into the editor. And this is really powerful because it basically means that we can visualize what the server and what the clients are doing at the same time, which is really handy. But there is a caveat, and that caveat is that the timestamps rarely match. And the reason they rarely match is because the actual logging code is dependent on the process lifetime. And you can actually see here, this is the function where it actually generates the log place. And you can see that it's literally just passing in the time in seconds for the world that's there. Now, that's fine, except for the fact that the server and the clients can be spawned at different times, and they can also have different load times as well. So if one of them is a lot faster, in our case, the server tends to spin up very fast and the client takes a bit longer to load up, then that time in seconds is not going to correspond together. And you can see that this is here. So here I start the logger at the start and then I fire up. So this is firing up a server and a client at the same time. It takes a little bit to spin up. And then we'll see that it starts populating the server a lot quicker than it does the client. So the server's spun up now. The server is already generating points. And we can see that the bottom track, the client, is actually offset by about 10 seconds or so. And when we visualize it, we have the animation for the tentacle coming out. We can see that for the green, for the server, it started there and it started emerging out really early. And then 10 seconds later, the client will play exactly the same animation. Now, actually, we have a bunch of syncing code which keeps them together, but according to the visual logger, they're massively disconnected, and we know that's not actually the reality. But it does mean that visualizing what's going on in the server and the client is now incredibly hard because they don't correspond to the same place in the timeline. So let's fix that. Our solution was to create a method for the application to supply a custom timestamp. So instead of relying on the time in seconds that the world was alive, we can provide our own time step for it. So this is how it was. It just used the time in seconds. So all we did was we created our own function, get timestamp for object. This is in the visual logger code here, so we're not writing any kind of application code at the moment. And then the function here, get timestamp for object, we basically can optionally supply it with a function, the get timestamp function. And if that function exists, then it will go and call through to that function and say, please give me the timestamp that I should be using for this particular entry. And if we don't supply that function at all, then it will just fall back to doing exactly the same behavior. So we don't have to use this functionality if we don't want to, but it's there if we do. And there's a function just at the bottom which allows us to set that function as well. And then this is our code. This looks kind of daunting, but it really isn't. So that we actually do this at the start of our game state code. So this is literally on boot up, effectively. We just set this function. We're using a Lambda. If you're not familiar with Lambdas, this will be a bit bonkers, but it's just a local function, effectively. We use the object as it comes through, and we get a service. Now, we've got a special service in CFDs called the time service. It's a replicated time that is authoritative, so it's the server's time that's replicated through to the clients. And we use this so that, for instance, we can sync all of our water together. So our water uses a fast Fourier transform to make these lovely waves, and that is effectively seeded on the global time. So we don't have to sync the water positions together. We just need to sync the time, and then all the algorithms will stay in sync. And that means we can use that authoritative time for both the server and the client, and we know that they correspond to the same thing. So this is exactly what we do here. We mod it within 10,000 only because we didn't want the timeline to get crazy big. Technically, that could cause issues when it wraps around, but in practice, we didn't really see any problems with it. And this is what it looks like. So here again, we got the same scene. We've got a single Kraken tentacle. So I hit record, and straight away we can see now that it's populating both the server and the client in sync. So we know that they correspond to roughly the same frame. And we know that there is natural latency between the client and the server already due to the way that it's replicating these things across. But we know then that this is effectively the synced up result that we're seeing. So let's just get rid of this tentacle, and then we can visualize what we've got in our log. There goes the tentacle, and then we can have a little look. So yellow's the server, green is the client. There you go. So you can go through it. Straight away, we can actually see it gives us quite a nice visualization of what the tentacle's doing at any one point. And we can overlay those two together, and we can kind of see what's going on. So you can see they are a little bit out of sync, which we would expect, server and client. But you can see they're roughly doing the same thing that's there. So solving an actual network bug with a visual logger. This is actually going to bring together all of the visual stuff that we've done together. So here we are. We've got the tentacle. So with this particular problem, actually, I'll just describe it first. So we had a designer, and the designer said, I keep getting my gun out, and I'm hitting a tentacle, and I can see the tentacle doing its hit reaction animation, but it's not killing the tentacle. The tentacle is not losing any health. So the bug came in as an invulnerable tentacle. It can't be defeated. So we used the visual logger to capture what was going on, and we were able to recreate it, and we could actually see what was happening here. So if I look at some of these tracks that are going on, I can see I've got a projectile trace at the bottom. Straight away, I can see that on the server's projectile track, the projectile keeps going forever, which seems to indicate that it's missed. Unfortunately, we can visualize some of these things. So here, we've got the client view. So the client view, here we go. We can see that the client has fired a projectile, and it's landed smack bang on the end of that tentacle. So it registers a hit on the client. Brilliant. It's working fine on the client. But now, if we visualize the server one, we can see it hits on the client, and the projectile misses the tentacle. So this is a classic network out of sync problem, where the time it takes to replicate the projectile and the tentacles are too out of sync. So we're not, what's happening on the server doesn't represent what the client has seen. In this case, the fix was actually relatively trivial, which is we have a natural offset that we offset the client and the server tentacles by, and we were actually just able to reduce it by a particular multiplier in order to keep them more in sync. And this is what this looks like. So this was the corrected and fixed version, which fixed the problem. You can see we've got a whole bunch of data there that's there. Let's get rid of the tentacles so we can have a little look what's going on. Whenever you're ready, tentacle, thank you. And let's visualize them together. So here we can see they're much tighter together. So there is still a little bit of a lag, but actually this is much closer to what we would expect. So theoretically, it was still possible if you really caught the timing right to to get the problem again, but most of the time they're nicely in sync. So we were able to do that, and actually we've been able to track down a number of these kind of player versus player and player versus environment problems by being able to capture it in the visual logger and have a look back through it. So that was a really quick run through. I hope that's been useful, and I hope it's given you some inspiration of some of the things that you can visualize. If some of the ways that we're working at Rare and Sea of Thieves, if that all sounds really exciting, then you can join us, because we're hiring. I know pretty much everyone says this after a talk, but if you are interested in finding out a little bit more about how we work at Rare, do come and find me or one of the others. And also, please catch my colleague Jessica Baker's talk in room 2 in a little bit. I forget exactly what time it is. 4:15, in which he's talking about automated testing and our culture of testing and how we avoided crunch during Sea of Thieves. It's really good. You definitely want to go and see it. Thank you, everyone. Go see Jessica Baker's talk, room 2, 4:15. Thank you.